Welcome back to JK Chemistry. Today we are going to deal with a comparative study about rotational spectroscopy versus vibrational spectroscopy. This is mainly designed for a competitive examinations like JAM, GATE, CSIR-NET. Let's start with the same. First, we want to know what is spectroscopy. Spectroscopy is nothing but it is the study of interaction between electromagnetic radiation with matter. അതായത് ഇലക്ട്രോമാഗ്നറ്റിക് റേഡിയേഷന് മാറ്ററുമായിട്ട് ഇന്ററാക്ട് ചെയ്യുന്ന സമയത്ത് എന്തൊക്കെ മാറ്റങ്ങൾ സംഭവിക്കുന്നു അതിനെക്കുറിച്ച് പഠിക്കുന്ന ഒരു ശാസ്ത്രശാഖയാണ് സ്പെക്ട്രോസ്കോപ്പി എന്ന് പറയുന്നത്. So the most important thing in spectroscopy is electromagnetic radiation. So we know about the electromagnetic spectrum. Electromagnetic spectrum is nothing but it is the arrangement of all the electromagnetic radiation in the sun rays. That is electromagnetic spectrum arranged in the increasing order of their frequency or decreasing order of their wavelength. So this is the typical spectrum. So let's see, we can see it start from high wavelength to low wavelength or low energy to high energy. So it is starting from high wavelength radiation. They are used in telecommunication, radio wave followed by microwave, then infrared, okay, followed by visible radiation. They are visible to us, followed by ultraviolet radiation, then X-ray, gamma ray. So this is the spectral order in accordance with their decreasing order of their wavelength or increasing order of their frequency. Why? Because the frequency and the wavelength are inversely proportional. So this is the trend. So it is start from high wavelength radio wave, then microwave, then infrared radiation, then visible light, followed by ultraviolet radiation, X-ray, gamma ray. So it start from high wavelength to low wavelength or low energy or frequency to high energy or frequency. Why? Because the most important equation, Planck's equation, that is energy of radiation is described by means of E is equal to h nu, where is the energy of radiation, h is Planck's constant, nu is the frequency, and the frequency again defined as nu is equal to c by lambda. Okay, fine. Now we have mentioned about electromagnetic spectrum. Now we want to know how to this radiation interact with the matter, or what are the changes happen during this interaction. Before that, we want to know what are the energy levels or what are the energy present in a matter. This is the high energy difference possessing electronic energy levels. This is the ground electronic energy level. This is the first excited electronic energy levels. Within these two electronic energy levels, we can see lower energy gap having another type of energy is called vibrational energy. So this is the lower vibrational energy. This is the first excited vibrational energy within the first electronic energy levels. In between these two vibration energy levels, we can see rotational energy levels. So electronic energy levels, then vibrational energy levels, then rotational energy levels. That means a matter having different kind of energy, that is electronic energy, vibration energy, rotation energy. Clearly this energy gap is different. So electronic energy levels having more electronic gap like this. That means we have different kind of electromagnetic radiation. So one of the electromagnetic radiation, that is UV radiation or visible radiation, they have the energy that is equal to this energy gap. That means when UV radiation incident on a matter, what will happen? What will happen? An electron from lower energy to higher energy level get excited, right, like this. That is, a UV radiation interacted with a matter and an electronic change will take place. That's why it is called UV visible spectroscopy or electronic spectroscopy. So electronic transition takes place, right. Now within these electronic energy levels, we can see vibration energy levels. When IR radiation in electromagnetic radiation interact with the matter, it will affect on its vibrational energy. That's why it is called IR spectroscopy or vibrational spectroscopy. So during this process, its vibrational energy changes. That is, vibration energy changes from low energy to higher energy. That means vibrational energy transition takes place. Now when we are going to this rotational energy levels, when the microwave in the electromagnetic radiation interact with this matter, what will happen? Its rotation energy changes. That's why it is called microwave spectroscopy or rotation spectroscopy. So rotational energy transition takes place during this process. So according to different kind of energy, different kind of radiation and different kind of energy, we can classify different type of spectroscopy, right. Here we are mainly deals with this vibration energy, vibrational spectroscopy and the microwave spectroscopy. That is, we can easily understand by comparing both these. Okay. So first rotational spectroscopy, second vibration spectroscopy. So in science, it is easy to understand when we are taking a model. So rotational spectroscopy, the model is a rigid rotator or rigid rotor. That is a ball having M1, M2. It is connected by a rod. So it is a rigid rotor. Okay. So the rigid rotor is the well-known model for rotational spectroscopy. So here we can consider all linear diatomic molecule like HCl. Okay. Here the physical quantity is moment of inertia is given by mu r square, where mu is the reduced mass, that is m1 m2 divided by m1 plus m2 r square. This is the most important equation here. Moment of inertia is equal to mu r square, where mu is the reduced mass, m1 is the mass of first atom, m2 is the mass of second atom. Okay. So mainly it is given in gram atomic mass. So we want to convert 1 gram atomic mass is equal to 1.67 into 10 raised to minus 27 kilogram. Then we can get exact value. For vibrational spectroscopy, model is vibrating spring. One of the end of spring is fixed, other end is mobile. So we can stretch or compress. According to Hooke's law, here the restoring force F is equal to minus kx, where k is the spring constant or force constant, x is the distance moved. So this can be analog with our molecule. Suppose I have a HCl molecule and I fixed Cl here, and I can stretch or compress hydrogen accordingly. So this kind of model we can analog with our linear molecule. Okay, these are the model. Next, we know that in microwave spectroscopy, microwave electromagnetic radiation is used. In IR spectroscopy, IR radiation is used. Now, the selection rule is that which kind of molecule can show this microwave spectroscopy or IR spectroscopy. In the case of microwave spectroscopy, the gross selection rule, that is condition, molecule should have permanent dipole moment. That is very important. A molecule which should possess permanent dipole moment, then it can show microwave spectroscopy. While in the case of IR spectroscopy, molecule should have change in dipole moment during vibration. That means all kind of bond can show this IR spectroscopy, okay, except a homonuclear molecule. Another thing is that we are moving to quantum mechanics. So later we can see, but in this situation I am stating the selection rule, that is quantum mechanical selection rule, that is delta J plus or minus 1, where J is rotational quantum number. We have learned different quantum number, azimuthal quantum number, principal quantum number. Same way, J is the rotational quantum number. It should be, change in J should be plus or minus 1. While in the case of IR spectroscopy, delta B plus or minus 1, that is vibrational quantum number plus or minus 1. Okay. Now the most important equation in these two cases. So this is very easy. That's why I am doing this comparison. You can easily understand. Okay. Rotational energy, that is EJ, is defined as EJ is equal to h square divided by 8 pi square I J into J plus 1, where J is rotational quantum number. It can have value 0, 1, 2, 3, etc. It is in joule, where in vibrational spectroscopy EV is equal to V plus half H omega oscillation joule, where V is vibration quantum number. It can have value 0, 1, 2, 3, etc. So it can analog with our most pronounced equation, that is E is equal to h nu. Okay, before h nu you can have this value, that is V plus half, where omega oscillation nothing but frequency of oscillation. Instead of nu we are using another term, another notation, that is nu oscillation. That's all. Okay. But in spectroscopy, energy is being expressed by means of centimeter inverse. So how can we convert joule into centimeter inverse? It is simple. You just divide energy in joule by Hc, that is EJ by Hc give you H divided by 8 pi square IC J into J plus 1 centimeter inverse. This is very important equation. Okay. Here same way you have to divide energy by means of Hc, that is EV by Hc V plus half omega oscillation centimeter inverse. Very clear. So you have to remember this equation. Rotational constant, that is another important variable parameter in rotational spectroscopy, and it is important parameter. It is coming from our previous equation, that is energy expression equation, that is B is defined as B is equal to H divided by 8 pi square IC centimeter inverse, where I is the moment of inertia, C velocity of light in centimeter, that is 3 into 10 to the power of minus 10 to the power of 10 centimeter per second. Right. B, and clearly we can see this rotational constant is inversely proportional to moment of inertia, and we know that this moment of inertia is directly proportional to reduced mass. So we can say B is inversely proportional to reduced mass. Now oscillation frequency, we have seen our expression, energy expression, that is omega oscillation, that is defined as 1 by 2 pi root K by mu in hertz. That is K is called force constant, mu is reduced mass. Okay. So in spectroscopy, this is mainly expressed in centimeter. Later be expressed in centimeter inverse. So we want to express this omega oscillation frequency in centimeter inverse. You just divide by C. That is, you will get 1 by 2 pi C root K by mu centimeter inverse. This is very important equation. You can see this omega oscillation is directly proportional to force root of force constant, and inversely proportional to root of square root of reduced mass. Okay, that is another implication from this equation. Now this is very important thing, that is isotopic substitution effect. That is, if you have HX bond, X can be oxygen, nitrogen, etc. I just replace this H by means of deuterium, what will happen? That is called the isotopic substitution effect. This is very important. You will have many questions based on this. We know that B is inversely proportional to I and B is inversely proportional to reduced mass. So clearly when we are having equation, that is rotational constant of Hx divided by rotational constant of deuterium substituted bond, that is dx. Clearly we know that B is inversely proportional to reduced mass. So we can have here I, that is I dash divided by I. That is I dash means moment of inertia of dx bond, and I is the moment of inertia of Hx. We know that it is inversely proportional. Okay, that is I dash by I. We know that I is directly proportional to mu. We know that I is equal to mu r square, right? So I dash, that is mu dash divided by mu. Okay. By doing approximation, you can have, this is approximately 2. That is very important. That is rotational constant of Hx divided by rotational constant of, or dx is approximately equal to 2. Okay, we know that mu is equal to m1, m2 divided by m1 plus m2 you can calculate, but you have to approximate. Okay. that is clearly you can take hx1, okay, 1 x, okay, you just to do approximation you can have two value. It's only approximate value, that is you have different options, so options having large difference, then you can do approximation, that you can use this equation. So every examination maybe it is approximate value. The same thing you can see in the vibration frequency, that is isotopic substitution effect in vibration frequency. We know that from our fundamental equation, omega oscillation, we can see that omega oscillation is inversely proportional to root mu, that is omega oscillation for hx divided by omega oscillation for dx is equal to square root of mu dash divided by mu. This is approximately equal to square root of 2. This is very, very important equation. You can remember this, you can do problem easily. Now the rotational energy levels and allowed transition. We know that different energy levels are there. Okay, we know that different energy. In rotational energy, that is rotation energy means energy within the vibration energy levels. You can see different rotation energy levels. So this is the ground state rotation energy level having energy 0B. First one, that here it is rotation quantum number 1. We know that energy expression is equal to B into J plus 1. By substituting J value, you can have the energy here, right? Okay, when J is equal to 1, you get 2B. Okay, so easily you can remember that is 2 into 3. 2 into 3. Okay, ready. Okay, next you will get 6B. Here it is 6B, not 3B. Here it is 6B. Okay, here it is 3 into 4, you will get 12B. Here it is 4 into 5, 20B. Here you will get 5 into 6, 30B. Here you will get 6 into 7, 42. That is the number in the J and number into number next. Okay, that is J into J plus 1, right? J into J plus 1, you will get to the corresponding energy. And this is the band corresponding to transition. The first band, that is the transition, corresponds to from J is equal to 0 to J is equal to 1. That is, this is the band corresponds to first transition. It having energy 2B. This is the band corresponding to the next transition, that is J is equal to 1 to 2 having energy 4B. Okay. Next transition, that is you can have the difference 2B minus 0B, that is 2B. Here it is 6B, not 3B. 6B minus 2B, you will get 4B. Okay, same way you can calculate. So these are the band and these are the spectrum. Okay. Here the selection, we already mentioned quantum mechanical selection rule, that is delta J is equal to plus or minus 1. That is you can have transition only by one difference. If it is plus, it is called absorption. If it is minus, it is called emission. Okay. The main implication that in this spectrum you can see these bands are differ by the 2B. That is very important. Two lines are differ by 2B centimeter inverse. Okay. The same way you can see vibration energy levels and allowed transition. Here the selection rule is plus or minus 1. Delta V is equal to plus or minus 1. Same way here we know that it is simple harmonic oscillator. So you can have this kind of energy diagram from half is equal to kx square. That is its equation. It is quadratic equation. Okay. This kind of curve you will get energy potential energy curve, and here it is internuclear distance. On a y axis it is energy, x axis it is internuclear distance. Okay, and here it is equilibrium, means that is bond length. For if you are taking HCl, this much length is called bond length. Okay, or equilibrium. And this is the ground state. It is the ground state. V is equal to 0. That is ground state vibrational energy. Ground state vibration energy. V is equal to 1, 2, 3. Corresponding energy you can calculate by using our equation. That is, we know that V plus half omega oscillation bar. When V is equal to 0, you will get half omega oscillation. When V is equal to 1, you will get 3 by 2, 2, 5 by 2, 3, 7 by 2, 4, 9 by 2, 5, 11 by 2, etc. Okay. According to selection rule, you can have only transition by one difference. The thing is that in this spectrum, you can have only one band, that is all the transition having a difference of difference of omega oscillation, that is 3 by 2 minus 1 by 2 omega oscillation bar give you omega oscillation bar. So for every transition you can have only one band having energy omega oscillation. So single line at omega oscillation centimeter inverse. Here you can have different transition having different energy, but here all the transition having allowed transition having a particular energy, that is omega oscillation bar. Okay, so that is another important comparison. Okay, now again you can have an isotopic effect in energy. Okay, energy in isotopic energy effect, that is the same equation you can see. This is the energy equation for rotational energy, that is Ej is equal to B into J plus 1. B is H divided by 8 pi square IC. So instead of we have substituted B. Clearly you can see E is proportional to B. Then we can take our earlier equation, that is isotopic effect on B, that is E Hx divided by E dx is equal to B Hx divided by B dash dx. That is nothing but I dash divided by I, that is equal to mu dash divided by mu, that is approximately is equal to 2. Now, the another important thing is that in vibrational spectroscopy you can have another important thing, that is 0 point energy. That is energy when V is equal to 0. That is even at ground state a molecule having some kind of vibration energy, that is called 0 point energy. That is E0 is equal to half H omega oscillation in Hertz. In centimeter inverse it is half omega oscillation bar centimeter inverse. That is very important, half omega oscillation bar in centimeter inverse. Same way isotopic substitution effect play here. We know that energy is directly proportional to omega oscillation. So we can derive this equation, that is E0 Hx divided by E0 dx is equal to omega oscillation Hx divided by our previous equation omega dash dx, that is equal to root of mu dash divided by mu, that is approximately 2. This is very important. So you can easily understand these two spectroscopy by this comparison and you can easily learn. Okay, now we can go through some problem. This is the first problem. For a diatomic molecule AB, the energy for the rotational transition from J is equal to 0 to J is equal to 1. That means first transition is 3.9 centimeter inverse. The energy for the rotational transition from J is equal to 3 to J is equal to 4 state would be. Okay, given is the energy for first transition, that is 0 is equal J is equal to 0 to J is equal to 1. You want to calculate the energy for a transition from J is equal to 3 to J is equal to 4. We know that the rotational spectrum, that is here the first band corresponds to first transition, that is 0 to 1. Second is 1 to 2. Third is 2 to 3. And next one is 3 to 4. So clearly you can have the energy for J is equal to 3 to J is equal to 4 is 8B. So you want to calculate B, but you have given is that 3.9 corresponds to J is equal to 0 to 1. So clearly this is the transition, first transition. So energy is 2B, right? So 2B is given. So delta Ej is equal to 1. Ej is equal to, that is 2B is given. That is 3.9. From that you can have B is equal to 1.9 centimeter inverse. Clearly you can calculate 8B, that is 8 into 1.9, that is equal to 15.6 centimeter. Very simple question, but you have to know the concept. Okay, so your option is D, right? Next problem. In IR spectrum of COCN H3 minus, the C cobalt H stretch is observed at 1840 centimeter. You may ask the COD stretch in COCN D3 minus. Okay, that means you are given with one complex, and the thing is that hydrogen is replaced by deuterium. So it is nothing but isotopic substitution. Okay, without knowing the concept, you may see it seems to be very difficult, but we have learned isotopic substitution. This is nothing, you are given a complex, simply complex for confusion. Okay, so clearly it is isotopic substitution. You want to calculate omega oscillation bar for COD. So we know that omega oscillation Hx divided by omega oscillation dx approximately root 2. Okay, so clearly here the given value is omega oscillation for Hx. You want to calculate omega oscillation bar for dx. So clearly omega oscillation dx is equal to that is omega oscillation for dx Hx divided by root 2, that is 180. 1840 divided by root 2 means 1.414, that is 1300 watt. It is approximately equal to 1300 centimeter. So clearly you can see all options are having different large difference, 1300, 1400. So clearly you can choose option A. Okay. So thank you. Like, share and subscribe.